Hi everybody, this is Chris Collison talking to you again today about how we might make some dilutions and quantitatively how we go from a concentrated stock solution to a dilute solution that we may use in a particular experiment. You'll go on to use this particular approach a lot in the coming months, in the coming course. Some examples follow, so work through those examples yourselves. And also, at the end, I'm going to tie this all back to quantitative stoichiometry and how we want to work from measuring out grams on a balance, converting that into a number of moles, or building a solution, a stock solution from that number of grams. But ultimately, we end up in moles of a reactant, and then we end up working through a reaction until we end up getting moles of product, which we then convert into grams of product in a yield. And of course, concentrations also result if we're working with chemistry in solution. So enjoy, and this will become very valuable for you as you work through the rest of the course. Thanks.
So here's the example. You have a stock solution. The stock solution has a concentration of 2.51 moles per liter. Again, the capital M for molarity, that is equivalent to moles. It's defined as being moles per liter. That's our definition. Let's use moles per liter because it's more helpful and it helps us remember the equation for concentration being equal to moles divided by volume. Okay, so here's our stock solution of concentration 2.51 moles per liter. We need to make a 0.0500 moles per liter solution in order to run a particular experiment that we're working on. So the question is, how much of this stock solution will we need to add to that 250 milliliter volumetric flask in order to make up that dilute solution of 0.0500 moles per liter? So let's write out the equation that we care about. Let's actually try it now. C1V1 equals C2V2 here. And let me just show you how straightforward these particular calculations are. If we always remember C1V1 equals C2V2, we're going to save a ton of time in this lab. So let's start with, for example, our stock solution. Okay, so we've got a stock solution and the concentration of that stock solution is 2.51 moles per liter. We don't know what the volume is at this point. We don't know how much stock solution. Remember, we're being asked how much stock solution we need. So we're going to just keep that as V1 in here. Okay, there's V1. We have V1 being equal to C2. What's C2 in this particular case? It's the final concentration that we need. So that final concentration is going to be 0.0500, and that's going to be again in molar, but I'm preferring moles per liter because those units are much more instructive to me. And we're going to multiply that by the final volume. Well, the final volume is going to be the volume in this volumetric flask. It's 250 milliliters. So in fact, let's keep it as 250 milliliters. Okay, we can convert that to liters. Okay, we will show, however, that in fact this particular equation can be used without converting the units, because recognize that on both sides we can cancel the moles per liter on both sides and cancel from one another, and what we're left with is perhaps a really simple equation here. V1 is equal to 0.0500. We're going to do some algebra, so we're going to divide this now by 2.51, because we brought this 2.51 over to the other side, and that's multiplied by 250 milliliters. So actually our answer, since we've cancelled out the moles per liter, the answer is going to be in milliliters in here. And when we throw this value into the calculator, what we end up getting is simply 4.98 milliliters. I've shown a little shortcut in here. Another way you can do this is by converting backwards and forwards from milliliters to liters. This is perhaps a better option because we're really always going to be working with the System International unit of liters for volume. And so 250 milliliters, of course, is 0.250 liters. The answer would come out the same. Okay, if we did that in the same way, so V1 equals now 0.0500 divided by 2.51. And we multiply that by 0.250 liters. We'd of course get a smaller number. We're going to expect a smaller number, and that would end up being 0.00498, and the units there would be liters. So again, when we can convert back to milliliters, we multiply by 1,000 milliliters per liter. In fact, that would end up giving us exactly the same number. Since this is used so frequently, let's do one more quick example here. If you dilute 25.0 milliliters of 1.50 molar, that's 1.50 moles per liter of hydrochloric acid. So we're going to dilute this stock solution. So our stock solution is going to be, here's V1. This would be our concentrated stock solution. This would be our initial concentration, so we'll call that C1. What are we going to dilute it down to? We're going to make that up to a volume of 500 milliliters. So the 500 milliliters will be our V2. It's going to be the final volume that we care about. And now we're being asked to calculate what the molar concentrations, that's moles per liter of the dilute acid. We're being asked to calculate what C2 is. So we don't know what C2 is. Let's remember our very simple expression, C1V1 equals C2V2. Okay, another way of writing this, of course, would be concentration of the concentrated sample, or the molarity of the concentrated sample. I guess we could put in there the molarity of the concentrated sample multiplied by the volume of the concentrated sample, and that would be the molarity of the dilute sample multiplied by the volume of the dilute sample. So this is a little bit more of a mouthful, more to remember. C1V1 equals C2V2. You'll take that with you wherever you go. Very easy to remember. Let's use this approach. So C1, we've recognized that that is 1.50, and we're going to use in here moles per liter again. Multiplied by the initial volume. The initial volume here is given in milliliters. Let's go back and convert this to liters, 0.025, and that's in liters. And that is going to be equal, that of course is equal to a number of moles, right? Because we're going to cancel these liters in here. We can cancel those liters, and we know that the number of moles is going to be the same after we dilute it, because again, we're just adding water as we dilute it down. We're not changing the number of moles of the analyte. So this is why we know this particular expression works. So let's get rid of those cancellation lines for the time being, and let's come back to C2. Remember, this is our unknown. We don't know what C2 is. Multiplied by V2, we do know what our V2 value is, and that's going to be 500 milliliters, or in liters that ends up being 0.500 liters. Another thing to think about, once we've cancelled the liters from both sides, we're going to end up with a moles per liter. That makes sense because our solution in here, we expect to have a concentration in terms of units, moles per liter. Let's clarify this now. Okay, what we care about is C2. Therefore, so this is really simple algebra from now on. So it's 1.50 moles per liter multiplied by 0.025 liters divided by 0.500 liters. Okay, and so that answer ends up being, when we throw it in the calculator, 0.075 moles per liter. Okay, and that's the final answer. That's our molar concentration that we'll end up with of the dilute acid. C1V1 equals C2V2. Coming full circle, this is a good image to remember. This basically is a flow chart of how we go through and carry out our quantitative stoichiometry or quantitative yield calculations, and often we're going to be working with solutions. And again today I've also talked about how we can use a stock solution to develop a dilute solution, and how we know how many milliliters of that stock solution we need to make or use rather for the final solution, and how we basically move between initial concentration, initial volume, and final concentration and final volume. So good luck. You will use this time and again. Come back to this as a resource, but thank you for listening.